Hello students. So we had started our discussion on alkyl and aryl halides. So this is our second session. In the first session, we had discussed about the preparation of alkyl halides. So if you have not gone through that session, please watch that session and then you can look at this session. Okay. Now, so today in this session, we'll be discussing about the nucleophilic substitution reactions. So nucleophilic substitution reactions. Okay, now which are generally referred as SN reaction. S stands for substitution, N stands for nucleophilic. So we'll be discussing about the nucleophilic substitution reactions of alkyl halides. What is a nucleophile? See, nucleophile is a nucleus loving species. Philic means attraction. An atom or a group of atom that gets attracted towards the nucleus. You know that nucleus carries a positive charge. Obviously, if a atom or a group of atom is getting attracted towards a positive charge, then it should possess negative charge only. So nucleophiles are generally electron rich species. Electron rich centers are called as nucleophiles. So nucleophilic substitution reaction involves the replacement of atom or a group of atoms by a suitable nucleophile. Okay, now let us take an example let us study this nucleophilic substitution reaction with respect to these alkyl halides. When I say an alkyl halides, there will be alkyl part and there will be an halogen part. When you compare the electronegativity of carbon and halogen, halogens are generally more electronegative than carbon. As a result, this shared pair of electron gets slightly displaced towards this halogen atom. As a result, halogen acquires a slight negative charge and this carbon acquires a slight positive charge. So this carbon halogen bond in an alkyl halide is polar, and the polarity is due to the electronegativity of this halogen atom as compared to the carbon. Okay, so if this alkyl halide is treated with a nucleophile, see, nucleophiles are electron rich centers, so a nucleophile may be neutral or it may be negative charge. It may be negative charge or a neutral. For example, OH minus. OH minus is a nucleophile. If we take an example of ammonia, ammonia is also a nucleophile, even though it is neutral because it contains lone pair of electron. Even water is also nucleophile because it contains lone pair of electrons. So a nucleophile may be negatively charged or it may be neutral. If it is a neutral, it should contain an unshared pair of electrons. So the nitrogen containing compounds generally behave as nucleophiles. Okay, so a nucleophile may be neutral also. The only condition is it should be an electron rich center. So whenever this alkyl halide is treated with a nucleophile, the nucleophile attacks this carbon. Why it attacks this carbon only? Because this carbon carries a positive charge. This carbon carries a positive charge. So this presence of this partial positive charge on carbon makes it susceptible to a nucleophilic attack. Thus, when a stronger nucleophile approaches the positively charged carbon of an alkyl halide, the halogen is readily displaced as an halide ion. So this halogen goes off as an halide ion. So it results in the formation of this carbon. So this nucleophile takes the position of the halide ion. So this type of reactions are called as nucleophilic substitution reactions. Okay, now if you consider the reactivity order, okay, reactivity of the halide ions, so iodoalkanes, that is iodoalkanes, I mean Ri, are more reactive than bromoalkanes. Bromoalkanes are more reactive than chloroalkanes, which are more reactive than fluoroalkanes. So the reactivity order is like this. So iodoalkanes are generally more reactive. The reason for this is because of the bond dissociation energies. So here the bond dissociation energy is very low, so it can be easily cleaved, whereas here the bond dissociation energy is little high. For if R is a methyl group, then methyl iodide, the bond dissociation energy is 234, okay, kilojoule per mole. Here it is 293, here it is 351, and here it is 452. So as we move, the bond dissociation energy is increasing. Bond dissociation energy is nothing but energy required to break the bond. So as the energy required to break the bond increases, so the reactivity decreases, because we require more energy to break the bond. That means the bond does not cleave easily. So if the bond cleaves easily, then only a nucleophile can attack easily. So that's why iodoalkanes are generally more reactive. So this is the basics regarding the nucleophilic substitution reactions. We come across several nucleophiles. So to give you some examples, I have given OH minus, ammonia, water, even cyanide is a nucleophile. So there are several nucleophiles that are there. So that are some of the nucleophilic reactions are there for your syllabus. So those nucleophilic reactions is what we are going to discuss. So let us first start with the replacement by an hydroxyl group. Okay, hydroxyl group. Now, for example, if we have an alkyl halide, okay, if we treat this alkyl halide with OH minus, OH minus can be obtained from KOH, it can be obtained from NaOH. So when alkyl halides are treated with aqueous KOH, okay, or moist silver oxide. Moist silver oxide is nothing but AgOH. Okay, silver hydroxide it is. Moist silver oxide is nothing but it will be in the form of silver hydroxide only. When an alkyl halide is treated with an hydroxyl ion, so this OH minus attacks this, resulting from the formation of ROH plus X minus. So generally alcohols are formed. Okay, now for example, if you treat this C2H5Br, that is ethyl bromide, if you treat this with KOH, that is aqueous silver hydroxide. C2H5OH plus KBr. So instead of treating it with KOH, if you treat it with silver hydroxide, that means moist silver oxide, you are going to get the same product. If you treat it with water also, you are going to get the same product only. So this reaction is replacement by hydroxyl group. Okay, it results in the formation of ethanol. This is ethanol. Okay, this is also a nucleophilic substitution reaction where OH minus replaces this Br. Okay, this is one such reaction. We will deal with other reactions also. Now, we have here preparation of cyanides, isocyanides, nitrites, and nitro compounds, as well as we come across preparation of ethers also from nucleophilic substitution reactions. Okay, before going to that, let us just discuss about some nucleophiles which are called as ambidentate nucleophiles. So what are these ambidentate nucleophiles? So ambidentate nucleophiles are the nucleophiles which contains electron pairs on two atoms. That means they contain two donor atoms, but donation takes place through one of the atom. Ambidentate, ambiguity, a state of confusion is called as ambiguity. Let's take an example of this cyanide. In a cyanide carries a charge of minus. Nitrogen contains a lone pair of electron. So here carbon can be a donor as well as nitrogen also can be a donor. So such nucleophiles are called as ambidentate. That means, see, the electron pairs are present on both carbon as well as nitrogen. Attack can take place through carbon or attack can take place through nitrogen. It depends upon the reagent that you have taken. If attack takes place through carbon and alkyl group bond will be formed, you get cyanide. If attack takes place to nitrogen, isocyanates will be formed. Let us go through these examples now. See, we have two reagents. One is potassium cyanide, other one is silver cyanide. See students, potassium cyanide is an ionic compound. Okay, potassium cyanide produces free cyanide ion. It produces free cyanide ion. So where carbon carries a negative charge. Hence, when potassium cyanide is used, attack takes place through carbon only. But AgCN is a covalent compound. AgCN is a covalent compound. It doesn't produce a free cyanide ion. As a result, what happens if the attack takes place? The attack cannot take place through carbon. The attack will always take place through nitrogen only. So if you are using potassium cyanide, then carbon attacks. If you are using silver cyanide, then nitrogen attacks. This is the basic difference. We're getting this. For example, now you have an alkyl halide. You are treating this alkyl halide with potassium cyanide, and you are using the same alkyl halide with silver cyanide. See what happens, you see. So here potassium cyanide dissociates to give K plus Cn minus. So carbon carries a negative charge. This carbon will attack this. So you get this compound. You get alkyl cyanides. Or even you can call them as nitriles. Okay, cyanide Cn or nitriles. You can even call them as nitrile. But if you use AgCN, the attack takes place through nitrogen only. The attack takes place through nitrogen only. So you get this compound RNC. You get alkyl isocyanide. So you can prepare even cyanides or isocyanate. It depends upon the reagent that you are using. Okay, let us take some specific examples. I will just go forward with some specific example. Ethyl bromide. Okay, ethyl bromide. When it is treated with, okay, potassium cyanide, when it is treated with potassium cyanide. Okay, alcoholic potassium cyanide is what you can take. Okay, potassium cyanide K plus Cn minus, right? So this Cn minus attacks the carbon. It attacks the carbon. So when it attacks the carbon, Br goes off. So you get C2H5 C as usual, triple bond N. Triple bond N plus KBr is what you get. Okay, you get this compound. Ethyl cyanide is what you can call it as. Ethyl cyanide. Okay, now if you use the same, I will just write it as CH3CH2. okay, C2H5 can be written as CH3CH2 Br. If we treat it with AgCN, what happens? Nitrogen attacks because it does not ionize. So nitrogen attacks, right? I've said that nitrogen attacks this carbon, Br goes off. So a bond between this and this nitrogen will be formed. So this bond breaks, right? That carbon that comes here. So what you get? You get CH3 CH2 N triple bond C. Nitrogen has donated electron. So you get isocyanates. Okay, you can call this as ethyl isocyanide. Ethyl isocyanide is what you get. So this is an ambidentate nucleophile. So attack can take place through carbon or attack can take place through nitrogen. It depends upon the reagent that you are using. We come across another ambidentate nucleophile, that is NO2. NO2 minus is another ambidentate nucleophile. So you can even get nitroalkanes or alkyl nitrides also. Alkyl nitrides. Let us go through those examples also. Okay, now. So replacement by nitrite group. Okay, now same students. CH3 CH2Br. If I treat this with KNO2, potassium nitrite. Potassium nitrite. Potassium nitrite is like this: K plus O N double bond O ionic. Same CH3 CH2Br ethyl bromide plus silver nitrite. Here it is ionic, so the attack takes place through oxygen. Attacks takes place through oxygen, resulting in the formation of this compound. CH3 CH2 O N double bond O, as usual KBr. So you get ethyl nitrite. That's the product. Right? Now, if you use silver nitrite, an ethanolic solution of silver nitrite, ethanolic aqueous solution, C2H5 OH bar water, that is used as a solvent here. So it does not dissociate. So the attack takes place through nitrogen. Nitrogen attacks. So it results in the formation of CH3, CH2, N. So when a new bond is formed, this goes off. Ag combines with Br to form AgBr. That's a different thing. Now this attacks here. So nitrogen is forming a new bond, hence the nitrogen acquires a positive charge. This is what I get. This is nitroethane. Nitroethane. So look at two different products, right? One is nitrite, other one is nitro. So this can be also referred as an ambidentate nucleophile only. Okay. So this is about the replacement preparation of cyanide, isocyanide, nitrite, as well as the nitro compounds also. The last one, we come across a replacement by an alkoxy group that results in the formation of ethers. Formation of ethers. That is replacement by an alkoxy group. Okay. Whenever an alkyl halide is treated with sodium alkoxide, sodium alkoxide is nothing but RONA, RO minus Na plus, alkyl group and oxygen, alkoxide. So this can be prepared by a reaction between alcohol and sodium. Okay, sodium alkoxides can be obtained. Right now, sodium and alkyl halide, when it is treated with sodium alkoxide, okay, sodium alkoxide, this O minus attacks this R and this goes off. ROR. What we get is ethers. Right? I'll take just an example. CH3, CH2Br, when it is treated with sodium ethoxide. This is sodium ethoxide. Sodium ethoxide. What happens? This is C2H5O minus, this is Na plus, this carries a partial negative charge and a partial positive charge. Obviously, this oxygen will attack here. So it results in the formation of this compound. CH3, CH2O, this part, C2H5. Right? So this is an ether. Plus the side product will be NaBr. So this is diethyl ether. This is an ethyl group. This is also ethyl group. So this is called as diethyl ether. This method of preparation is called Williamson's. This is called Williamson's ether synthesis. This is called Williamson's ether synthesis. That is when an alkyl halide is treated with sodium alkoxide, it results in the formation of ether. So this preparation method is called as Williamson's ether synthesis. Okay. So these were the few nucleophilic substitution reactions that are prescribed for a syllabus. Okay. So this was about today's session, students. In next session, we'll be discussing about SN1 and SN2 reactions. What we mean by SN1 and what we mean by SN2 reactions. Okay. Thank you.